the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through a concept called coordinate systems. And this is not like coordinate systems from your old algebra course. Here we're transforming vectors from abstract vector spaces into a very familiar vector space for us, which would be Rn. And this is what this note is saying. Before we go too far, let's recall that we're no longer necessarily dealing with vectors in Rn. Our vectors are now from vector spaces such as P sub n, F, or other more abstract spaces. And if you don't know what those are, you should probably rewind to the previous video where I just talked briefly about them. Now, just to drive the point home, you can tell that I'm really trying to get you to buy into this. As we stated in a previous video, the last video in fact, we are going to take a vector x from V, which is an abstract vector space. It's not going to be Rn for this specific discussion right now, just because I find that allowing V to be Rn or something like that starts to muddy the waters. So I'd like to have a clear delineation of what we're talking about. So let's just assume that V is an abstract vector space for right now. And we want to find a way to write a vector from that abstract vector space V as a vector from Rn. To do this, we'll need some common language, and that language is listed below. Coordinates relative to the basis. By the way, this video is going to be somewhat short because all I want to do is introduce this language. It's big enough language right now that it probably takes a full video to really get it. So suppose that we're given a set of vectors B that form a basis. And this basis is to our abstract vector space V. And also suppose that we have some vector x that we pull from that abstract vector space V. Now remember, from our previous video, x has a unique representation as a linear combination of those basis vectors from B. We will define the coordinates of that vector x relative to the basis B as the weights of that unique representation in terms of the bases. Now, up to this point, this should not be too crazy. All I'm saying is, we have basis vectors b1 through bn, and if they form a basis for our abstract vector space V, then there's some linear combination of those basis vectors that will give us x from that vector space V. What we're going to do though is we're going to call those weights, rather than calling them weights from this point forward, we are going to call them coordinates of x relative to that specific basis. That is, C1, C2, all the way to Cn are numerical values we can assign to this vector x from the abstract vector space V. Remember that abstract vector space V does not actually have to have column vectors like we're used to. It could be functions, it could be cars, it could be pictures, it doesn't really matter. The main thing is right now that we're creating a link between that very abstract space and the vector space Rn by creating an n-dimensional vector containing these numerical values C1, C2, all the way to Cn. So that vector we denote as the B coordinate vector in Rn. So we have started with a vector x in our abstract vector space, and we have no way to represent that abstract vector as a column vector. But if we just consider the fact that we have numerical coefficients that we previously called weights that we'd applied to the basis of that abstract vector space, and if we take those numerical coefficients and create a column vector out of those, then we have successfully mapped a quantity or an object from our abstract vector space into a very familiar vector space, which is Rn. And that combination or that column vector will be the B coordinate vector for that vector x in Rn. And this is how we call this here. So we just say that vector x, which yellow highlighted here from the abstract vector space, is now represented in our current number system, Rn, our current vector space Rn, by the b coordinate vector of x, which is a column vector of the weights. Now, just to let you know, somebody could come along and say, well, yeah, I know you have a basis for that abstract vector space, but there are actually many other bases for that vector space V. Well, this coordinate vector is only in reference to the current basis that we're working with, but if you want to change up the basis, that will also change up the weights on that new basis and will change up our new b coordinate vector. So the b coordinate vector is just from the perspective of what basis you're talking about at the time. By the way, the mapping that takes that vector from that abstract vector space, V, and maps it to our more common vector space, Rn, is called the coordinate mapping determined by the basis B. Now that's a very, very meaty definition. It's got a lot going on in there. So let's just quickly make up an example. Let's consider the vector space P sub 2, which is a vector space of all polynomials degree 2 or less over the real numbers. Now I hope you would agree there are no column vectors in that space, none whatsoever. It's just a bunch of polynomials. But what if somebody comes in the room and says, you know what, I have a basis for P sub 2, the building blocks for P sub 2. Let's pretend as though they hand us the basis 1, x, and x squared. Now I hope you would agree that linear combinations of those three functions, or what we would call three vectors in this vector space, will produce any polynomial up to and including a second degree polynomial. Now note, if somebody comes along and says, I'm going to grab a random vector from this very abstract vector space, well, that random vector, which is some function like this, and note, that is not a column vector, it's just some function, right? Because again, our vector space is full of functions, specifically polynomials of degree 2 or less. Well, by definition, we're going to say, you know what? Those weights, which right now we're saying are a sub 0, a sub 1, and a sub 2, will form a vector in R cubed. And there we have it. The b coordinate vector for x in R cubed is this beast right here. Notice the brackets on that x sub b right there. That's a clue that you are dealing with a column vector. That's us telling you as the student, us being the instructor, you being the student, that's us telling you that you started with a vector that might not have been a column matrix, but when you do the b coordinate vector to transform it into R cubed, that will be, according to these brackets, a column matrix. So we have now transformed an arbitrary vector from P2 into a world we're much more familiar with. So if somebody said, I need to take 5 times that vector x, I could just take 5 times this column vector in R cubed and then map it back here. We'll figure out how to do that mapping a little bit later. But for right now, I just want to get the idea down of what we mean by a b coordinate vector represented in Rn, and also what we mean by coordinates of x relative to the basis b. If somebody wanted to change the basis to a different basis for P sub 2, which there are different bases for P sub 2, an arbitrary vector from V can be represented as a linear combination of these vectors, but it takes a little bit of work. We actually did that in a previous video where we showed that that was actually a basis for P2, and we ended up showing that an arbitrary vector in P sub 2 could be written as a linear combination of those basis vectors using this relation over here. This is actually the easier relation to look at. So let me go back to our current work. So I could say, well, if somebody hands me a vector from V, well, they're likely not going to hand me a second degree polynomial that is already written as something times 1 plus something times 1 plus x plus something times 1 plus x squared. Luckily, we had already done all the work for that to arrive here, and you can multiply this out to make sure, but it does happen if you multiply everything out that this will compress all the way back down to a sub 0 plus a sub 1x plus a sub 2x squared. I promise. However, the coordinate vector for x with respect to this basis b, which I should probably call b bar. That way I don't confuse you with the second set of bases. This b bar coordinate vector for x in R cubed is the vector comprised of the coefficients of that linear combination. By the way, I hope you noticed there that I actually miswrote this, that b was supposed to be on the outside of the parentheses or the brackets, and same thing with this b bar. So I fixed it. But anyhow, that's a little deeper than what I wanted to do for right now, but you get the point. When I changed the basis from the simple standard basis, giving me this coordinate vector, to a different basis, a not so simple, non-standard basis for p sub 2, our coordinate vector will also change because it's with respect to that basis. So this showcases when you change the basis, the coordinate vector will change accordingly. Now we did all that hard work to arrive at a relatively easy problem, because really it should be that I do the easier problem first and then go into the harder problems. Sorry about that, but let's talk about this here. Let H be the vector space determined by the basis vectors sine of x, cosine of x. Well, first of all, since it's a basis for H, that means that every vector in H is just a linear combination of the sine and the cosine. And somebody comes in the room and they say, hey, I'd like you to write the vector x, which is the function -3 sine of x plus cosine of x, as a b coordinate vector in R squared. Now this will seem simple compared to the previous example. We just know that the vectors in H are not column matrices. They're not column vectors, right? So we like to transform them or pull them into R squared in such a way that they will become column vectors. And the way we do that is we take the weights of the basis vectors here, which are -3 and +1, and we create a vector in R squared from that. So the coordinate vector of x with respect to the basis b is going to be -3, 1. It's very, very fast to do. It essentially means go back 3 in the sine direction and go up 1 in the cosine direction. Of course, that is very abstract, but that's exactly what it means. So the punchline of this entire video is this. When dealing with an abstract vector space, if somebody hands you a basis and then they say, I need this vector written in terms of that basis to transform that over to our world, which is the world of Rn, well, since there's only really 2 basis vectors, we're going to go to R squared, and the coefficients of these basis vectors will form the coordinate vector in R squared with respect to the basis b for this vector x. It's actually very nice. Now, as I said, I only wanted to do a little bit in this video, and I wanted to keep it all about the abstract vector spaces, because if I had started this video talking about changing coordinates in R cubed to R cubed, it will muddy the waters significantly. So it's just better to start this way. The vector x here is from the abstract vector space. The coefficients of the basis vectors are going to be the entries for the coordinate vector in R squared. All right, I know that was a lot of talking. I hope it did help out a little bit, and I hope to see you in future videos. Have a great day. Be an awesome human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.